Welcome to G Fun Facts Online. In the grand theater of the universe, some of the most important characters are practically invisible. Today, we're talking about a particle so strange, so elusive, that it's been nicknamed the ghost particle. It's the neutrino. Billions of them are passing through your body every single second, yet they almost never interact with anything. For decades, they've held one of physics' biggest secrets because our best rulebook for the universe, the Standard Model, made a huge mistake. It said neutrinos should have no mass at all. We now know that's wrong, thanks to the discovery that they can shapeshift between different types, a trick that's only possible if they have mass. This single discovery broke open a new frontier in physics and kicked off a global race to answer a deceptively simple question: how much does a ghost weigh? To weigh a ghost, you need a very special scale. Enter the Karlsruhe tritium neutrino experiment, or KATRIN. Picture a colossal, 70-meter-long instrument in Germany, built with one single, incredibly difficult purpose: to pin down the mass of the neutrino. Its method is pure genius. Scientists watch a radioactive type of hydrogen, called tritium, decay. When a tritium atom decays, it spits out an electron and a neutrino. Think of it like a tiny energy budget. This budget is split between the two particles. If the neutrino had zero mass, the electron could theoretically take the entire budget. But because the neutrino does have mass, it always carries away a tiny crumb of energy for itself. This means the electron's maximum possible energy is always just a little bit less. By measuring the energy of millions upon millions of these electrons with unprecedented precision, KATRIN can figure out how much energy the ghostly neutrino stole, and from that, deduce its mass. And in April 2025, they announced a new record. They have now confirmed that the neutrino's mass cannot be more than 0.45 electron volts. To put that in perspective, that is less than 1/millionth the mass of a single electron. It's a staggering achievement, providing a hard upper limit from a direct measurement right here on Earth. But weighing a neutrino isn't just a job for labs on Earth. We can also use the entire universe as our scale. You see, while one neutrino weighs almost nothing, there are a lot of them. Around 300 of them in every single cubic centimeter of space, right now. All that mass, tiny as it is individually, adds up. And on a cosmic scale, that collective mass has a powerful gravitational influence. It helps shape the entire structure of our universe, the vast, web-like pattern of galaxies and galaxy clusters we call the large-scale structure. Here's how. Back in the early hot universe, neutrinos were zipping around at nearly the speed of light. As gravity began pulling matter together to form the seeds of galaxies, these speedy neutrinos just wouldn't get trapped. They were too fast, too slippery. They effectively streamed right through these growing clumps, smoothing out the distribution of matter on smaller scales. The more massive the neutrinos are, the stronger this smoothing effect would be. Cosmologists can see the signature of this effect in two main places: in the faint afterglow of the Big Bang, called the cosmic microwave background, and in the precise 3D maps of millions of galaxies created by surveys like the Dark Energy Spectroscopic Instrument, or DESI. So now we have two different ways of weighing the ghost particle: the direct, hands-on approach of KATRIN on Earth, and the vast observational approach of cosmology. And this is where the story gets really exciting. On one hand, the results agree beautifully. The cosmic measurement, which suggests the total mass of all three neutrino types is less than 0.12 electron volts, fits perfectly well under the hard limit set by KATRIN. This is a huge win for science. It means our understanding of physics works both in the lab and across the cosmos. But on the other hand, a fascinating tension is building. From other experiments, we know that the total mass of neutrinos must be at least 0.06 electron volts. The cosmic measurements are now pushing the upper limit down so far. Some analyses suggest it could be below 0.073 electron volts, that they are getting uncomfortably close to that floor. We're left with this incredibly narrow crawl space where the true value must lie. If those cosmic measurements get any tighter, they could clash with the established minimum value. This isn't a crisis. It's a clue. A tension like this is exactly what scientists look for, because it could be pointing the way to brand new, undiscovered physics, perhaps hinting that our model of the universe is incomplete, or that neutrinos have other strange properties we haven't even dreamed of. The quest is far from over. KATRIN will continue taking data, pushing its limits even further, and its facility is already being upgraded to hunt for even more exotic particles. At the same time, a new generation of cosmic surveys, like the Euclid satellite, will map the universe with even greater precision. They promise to squeeze that crawl space for the neutrino mass even more, potentially giving us a definitive answer. The mass of the neutrino, a number so small it's hard to even imagine, connects the world of the tiniest particles to the grandest structures in the cosmos. It's a portal to physics beyond our current understanding, and the search for it shows science at its best. Two completely different fields, particle physics and cosmology, converging on one of the universe's greatest secrets. The story of the ghost particle is just getting started, and you can be sure we'll be watching.